All right, guys, we got lesson 2.2.2 ready to change. We're going to split this one up into 2 days because there's a lot of stuff to digest on this one. So what we're going to look at is rates of change. And we're going to look at it by looking at a race and trying to graph it and see what we can find out about rates of change through the graphing of it. So we've got this race. It's going to be done in a couple of heats. So, it's a couple of different races before you get to the championship round or whatever. This is a tricycle race because, tricycle races are a big thing, I guess. So we've got this race going on. And in our first heat, we've got 3 contestants. We've got Leslie. Leslie's going to start at the starting line, which is a good place to start. And then her rate is she's going to be traveling and pedaling her little legs as fast as she can go on her tricycle. 2 meters every second is how fast she's going to go. That's her rate. So for every second, she can go 2 meters. And then next up, we've got Kristin. Kristin, they're going to give a head start to her. So 8-meter head start. So she's not starting the starting line. She gets to start a little bit ahead. And her rate is 2 meters, but every 5 seconds. So you can see already that Leslie's going way faster than she is. So it takes Kristin 5 seconds to go as far as Leslie can go in 1 second. And then we got Evie last. Evie is going to get a 6-meter head start. And her rate is 5 meters, but it's every 4 seconds. All right, what we want to do is we want to write an equation for each of these and then make a graph. Now, a lot of these types of problems, when it's like a word problem, you've got to decide what your x variable is going to be and your y variable. And when we get this word per, it's really telling us what should be our x and y, because meters per second is a ratio or a fraction. It's saying meters over seconds. That's what the per word means, is it's meters per second. And we know from what we've learned about slope is that slope is the change in y over the change in x. So that's telling us that in this meters per second statement there, that meters should be the y value and x should be the seconds value. So we're going to keep that in mind when we make our graph, is that meters should be y and x should be seconds. All right, so looking at Leslie, let's do her in red. Leslie, we want to know her total meters, so it's going to be y equals, so meters equals, and then she's going to start at the starting line, so our intercept over here is going to be 0, because there's not going to be any, she's going to start at 0 for her meters. She's going to be at 0 meters when the race starts. And then she's going to be 2 meters for every second. So that's 2 meters times the number of seconds. And that's going to be her equation, y equals 2x. Her meters is going to be 2 times the seconds, because if you go 1 second, she's at 2 meters. 2 seconds, she's at 4 meters, and so on and so forth. 3 seconds, she's at 6 meters. All right, so 2 meters for every second. Next person, we've got Kristin. So let's do Kristin in light blue right here. So Kristin is going to be y equals, so her meters is going to be equal to, now 2 meters every second. We said earlier this is a ratio. So this is 2/5, 2 meters for every 5 seconds. And then we're going to multiply that by the number of seconds. So this means at 1 second, she's at 0.4 meters, because 2/5 is 0.4. Now she was given a head start of 8 meters, so we have to add that, because at 0 seconds, she'll be at 8 meters, because 0 times 2/5 is 0, 0 plus 8, 8 meters, 0 seconds. And then every second that passes, she gets 0.4 meters more. So at 1 second, she's at 8.4. At 2 seconds, she's at 8.8. All right, so keep on going like that. All right, so we've got kind of the pattern down here. I want you to fill in for Evie what her equation should be for hers. She's got a 6-meter head start, and she's going 5 meters every 4 seconds. So go ahead and fill in her equation real quick. Give you a couple seconds to think about it. All right, I'll do hers in green. So we're going to do y equals, her rate is 5 meters every 4 seconds, so that's a ratio of 5 over 4. So that's 1.25, that's what 5/4 is. So that means every second she's going to go 1.25 meters, but she gets a head start of 6. So this means at 0 time, she's already 6 meters ahead. And then at 1 second, we add 1.25. So she'd be at 7.25 at 1 second, and so on and so forth. All right, now we need to do a graph. Now let's look at the graph that I've made here. You probably want to break out some graph paper and start looking at it. Now here's how I set up mine. I've got time as my x-axis, and it's time in seconds. You always want what's being measured and the units that it's being measured. So this is time in seconds. And then on my y-axis, I've got my distance. And how is it being measured? Distance is being measured in meters. So you always want what's being measured and the units that's being used to measure it. Now notice that mine I only put in the first quadrant. There's a reason for that. I put it in the first quadrant because I figured we're not going to have negative seconds in this race, meaning we're not going to go back in time. You know, there's no time machines. It's just going to only be positive time that makes sense. Also, I decided that I wouldn't have negative numbers for my distance because we're going forwards, not backwards. Negative numbers for distance would mean that we're going in reverse, and I think they're all going to go towards the finish line instead of running away from the finish line. That would make sense to me at least. So we're going to just stick with the first quadrant here. All right, so now we're going to graph each of them. Our first person, if you remember, was Leslie. Leslie, it says she starts off at the starting line. The starting line is 0 meters. So I'm going to put at 0 seconds, she's at 0 meters right there. Now her rate was that every second she goes 2 meters. So at 1 second, she'd be at 2 meters. At 2 seconds, she'd be at 4 meters. At 3 seconds, 6. 4 seconds, 8, and so on and so forth. So I'll keep on putting in those points. 5 would be 10, and then 12. And then at 7 seconds, she'd be at 14. At 8 seconds, she'd be at 16. 9 is 18. And 10 seconds, she'd be at 20 meters. Now we have to ask ourselves is should we leave this as a discrete graph? Now a discrete graph would indicate that she's not allowed to have like half-second intervals. So at half seconds, she wouldn't be at any meter mark. Now a discrete graph like this would indicate that she is teleporting. So at 0 seconds, she's at 0, and then all of a sudden 1 second goes by, and then boom, magically she goes up to 2 meters. And that's obviously not what's happening. She's somewhere at 0.25 meters and at 0.8 meters. She's somewhere. So to show that she is somewhere at any second or fraction of second, we should make this into a continuous graph instead. Continuous graph means that all these other points, even though they're not whole number values, should still be available to us. So there I made her graph continuous because at half a second she would be at 1 meter. So fractions of seconds, decimals, they should be on this graph somewhere. All right, so there's our first person. We've got Leslie. All right, our second person, who was that? Our second person was Kristin, and she got that head start of 8. So let's do this in her color of blue. And then she's going to go 2 meters every 5 seconds. Okay, so head start of 8. So that means at 0 seconds, she's way up ahead of Leslie. So there's Kristin. At 0 seconds, Kristin's way back here at the starting line, and Leslie's way back here at the starting line, and Kristin's way up here at 8. Now it says that she's going to go 2 meters every 5 seconds. So she's going to go, we can do our slope triangle, 2 meters. So she'll be at 10. And when will she be at 10? At 5 seconds. So 2 meters every 1, 2, 3, 4, 5 seconds. And then we can do it again. 2 meters at 1, 2, 3, 4, 5 seconds. And let's just do one more because it's fun. 2 meters, 1, 2, 3, 4, 5 seconds. All right, so there we go. Now we've got Kristin. She started at 8, and then she went 2 meters every 5 seconds that passes. And we'll make hers continuous because we are assuming that she is not teleporting. Pretty cool if she was teleporting, but probably isn't. That must be a different race. All right, so here we got Kristin. Last person, I believe, was Evie. Yeah, it's Evie. Evie gets a 6 meter head start, and she goes 5 meters every 4 seconds. All right, on your own graph, I'm going to pause it here. I want you to figure out what her race would look like on the graph. She's starting off at 6 meters, and she's going to go 5 meters every 4 seconds. I'll go ahead and pause here, and then I'll show you what I've got. So 5, 4, 3, 2, 1. Pause yours. All right, so here I've got Evie. She started at 6, and then she was 5 over 4. So I went 1, 2, 3, 4, 5 meters, and then that's for 4 seconds. And then I did it again, 5 over 4, 5 over 4. All right, so there's Evie's race. Leslie's race is in red, and then in blue, we've got Kristin's race. All right, we're going to answer a couple of questions about our race. So I'll leave the graph up here, and let's look at what our questions are. First question about our race. After how many seconds did Leslie catch up to Evie? All right, so how many seconds did it take for Leslie to catch up to Evie? All right, so here's Leslie, and Evie is in green. So we can see here at 0 seconds that Evie's in the lead. After 1 second, Evie's still in the lead. 2 seconds, Evie's still in the lead. But we can see that the distance is closing between the two as we go. And then we see right here they're intersecting. They're intersecting at 8 seconds. So that means at 8 seconds, they are both at 16 meters. So the question was, how long does it take for them to catch up? Well, it looks like after 8 seconds, Leslie finally catches up to Evie, because at that time, they have the same exact distance. Second question is, how far were they from the starting line when Leslie caught up to Evie? Okay, well, we know it's 8 seconds that it takes them to get there. So 8 seconds, and they're at 16 meters. So they're 16 meters from the starting line because the starting line is 0. So at 8 seconds, they are both at 16 meters. So it took Leslie 8 seconds to catch up to Evie up there. All right, now the interesting part. How do we prove this algebraically? That at 8 seconds, they are definitely at the same spot. Well, algebraically, we look at these two. Here's Leslie and here's Evie. Now we're saying that at 8 seconds, their distance is the same. So what we want to do is prove that. So seconds is x. So I'm going to evaluate this equation for x equals 8 seconds. So I'm going to write y equals 2 times 8. So this means that at 8 seconds, what would be the meters? And we would get at 8 seconds, Leslie should be at 16 meters. All right, now to prove that they're at the same spot at 8 seconds, we would then evaluate Evie's equation for x equals 8 seconds, and then check to see if indeed she's at 16 meters at that point. So we're going to do y equals 5/4. We're going to evaluate for 8 seconds plus 6. Now 5/4, this is saying we're going to multiply by 5 and divide by 4. It's usually easier to divide by 4 first. So I'm going to take 8, divide by 4, that gives me 2, and then I'm going to multiply by 5. 5 times 2 is 10. So 5/4 times 8 is 10 plus 6, and it looks like they're both at 16 meters when we evaluated for 8. So we can see here algebraically that it says that when they have raced for 8 seconds, they are both at 16 meters. So that's when they caught up. We've proven it algebraically. All right, next question, who won? Well, just looking at our graph here, there is no indication of who won because at different times, people are at different spots in the race. What if the race was only 8.5 meters long? 8.5 meters long, it looks like over here, Kristin gets there first because it looks like at about 1.5 seconds, she makes it there. And then at 1.5 seconds, we can see that Evie right here is only about at 8 meters. And at 1.5 seconds, way down here, we can see that Leslie is only at 3 meters. So if the race was only 8.5 meters long, we could see that Kristin would be the winner. But later on, we can see that somebody else might be the winner. So we have to decide how long that race is. So how long is the race? The race is 20 meters long. So we want to find out who won the race. The first thing we're going to do is look at the graphs, and then we're going to prove it algebraically by looking at the equations. All right, so my race is 20 meters long. Where's 20 meters? Right up here. So I'm going to make a finish line at 20 meters. So here's my finish line at 20 meters. This is what they have to cross. And what we want to do to find out who won is find out who crossed the finish line first in the least amount of time. So it looks like Leslie's winning the race because she finishes the finish line, or she crosses the finish line at 10 seconds. Whereas Evie over here, she's crossing the finish line at a little bit over 11 seconds. So if the finish line's at 20 meters, Leslie finishes over a second before Evie does. And poor Kristin out here, wow. It's going to take her forever to get to the finish line. I didn't even make my line go far enough for her to make it. Poor girl. All right, now we want to prove that algebraically. So let's go ahead and pull this out here. Okay, algebraically, race is 20 meters long. Meters, is that X or Y? That would be definitely the Y value. So what this is telling me to prove it with my equation is to plug in 20 or evaluate 20 for Y. So I'm going to do that for each of them. Let's start off with Leslie in red. We're going to say that her Y value is 20, so I'm going to evaluate for 20. So I am substituting in instead of Y, 20, and then equals 2x. So remember, we're looking for x. That's the number of seconds. So I want to know what this is saying is how many seconds is it going to take for Leslie to get to 20 meters? And all I have to do is divide by 2, and we find out that x is equal to 10. So this means that Leslie's going to cross the 20-meter line at 10 seconds. Next person is Kristin. She's the one that's going super slow. All right, Kristin, when do you cross the line? So we want to know when she's going to cross the 20-meter line. So instead of y, we are going to substitute 20. And then her equation is 2/5 x plus 8. So for this one, I'm going to subtract 8 first and get, what's 20 minus 8 is 12. And then 2/5 of x. So remember, this is multiplying by 2 and dividing by 5. So to get rid of the 2/5, I'm going to multiply by 5/2. I'm going to do the reciprocal of that. Remember, this is multiplying by 5 and dividing by 2. So 12 divided by 2 is 6, and 6 times 5 is 30. So we find out for her, it's going to take her 30 seconds. So Leslie is going to finish at 10 seconds, do a couple of victory laps, and then later on at 30 seconds, 20 seconds after Leslie, Kristin's going to finally finish that race. Poor kid. All right, last one, Evie. We want to find out how long it takes her to get to 20 meters. So we evaluate for 20. And we do 5/4 x plus 6. So I subtract 6 from both sides and I get 14 equals 5/4 of x. All right, and I need to get rid of this 5/4, so I multiply by the reciprocal, which is 4/5. 5 does not go into 14, so I'm just going to do 4 times 14. Let's see, 28 and 56. So that's 56 over 5. So 56 over 5 seconds. Well, that doesn't really make a lot of sense, so let's turn that into a decimal. 5 goes into 5 once, and 5 goes into 6 once with 1 left over, so 0.2. All right, so we now know how long it took each of them to finish the race, because the race was 20 for each of them. And this tells us Leslie does it in 10 seconds. It tells us that Kristin does it in 30 seconds. And it tells us that Evie does it in 11.2 seconds. So who's the winner? Right over here, 10 seconds. That's the fastest person. So how long did it take each person to finish off the race? Well, we now know that it is Leslie with 10 seconds. We know that it is Kristin with 30 seconds. And we know that it is Evie with 11.2 seconds. So we got a winner here. All right, last thing we want to talk about is something called a unit rate. A unit rate is when our denominator is 1. So in this instance, we want to know how many meters for every 1 second. Well, we already have Leslie's in 1 second. She's 2 meters per second. So we would call that a unit rate because she's going 2 meters every 1 second. Over here, this is 2 meters every 5 seconds. That is not a unit rate, okay, because we want how many meters per 1 second. So this is asking what is Kristin's unit rate? Well, we can kind of see here that we've got it 2/5 times x. So her unit rate would be 2/5 per second. So she's blue. So she is 2/5 meters per 1 second, or just per second. And we can make that into a decimal and say that is 0.4 meters per second. Now, why do we want the unit rate? It's so we can compare everybody. Because if they're all being compared per second, we can see who the fastest person is. Leslie is 2 every second. Kristin is 0.4 every second. And if we worked it over here, we'd have Evie every 1.25 per second. So looking at unit rates helps us compare the different people with the same amount of seconds. So that's called a unit rate. It's every 1 second is, or every one of whatever the denominator is, to find the unit rate. Unit means one single unit. All right, so we're almost done here. We've got some questions that I want you to answer. And then I'm going to pause it and then have you come back and answer these. First question. We got a second heat coming up. All right, another set of racers. The line representing K's race is given by the equation f of x equals 2/3 x plus 1. What's her speed? And did she get a head start? All right, so I want you to answer those two questions. What was her speed? And speed we usually think of as unit rate. So what's her unit rate? And did she get a head start? All right, think about it. I'm going to pause in 5, 4, 3, 2, 1. So here's my answer. I said that her speed, or her unit rate, is 2/3 meters per second, or 0.6 repeating meters per second. And did she get a head start? Yes. Right here we see that she got a 1 meter head start. All right, second person. Elizabeth's race is given by the equation 12/16 x plus 4. Who's riding faster, Elizabeth or K? All right, so who has the faster speed, Elizabeth or K? Going to give you a second to answer it. 5, 4, 3, 2. Make sure to prove your answer. 5, 4, 3, 2, 1. All right, so here's my answer for the next one. Elizabeth is 12/16. I reduced that. 4 goes into both of those numbers. I reduced it to 3/4. So she's 3/4 meters per second. And if you're really good with fractions, you would know that that's faster. But it's usually better to look at it as decimals because you can definitely see the difference there. 3/4 is 0.75. So 0.75 is bigger or is greater than 0.6 repeating meters per second. So Elizabeth is faster because she's going 0.75 meters per second. And now you kind of see why that unit rate's important, is because now we can definitely see when we look at a unit rate who's going faster or what's the greatest rate between the two of them. All right, next question. Hannah's race is represented by this table right here. 14 seconds, she's at 10 meters. 28 seconds at 14 meters, 42 seconds at 18 meters. We want to know what her speed is. All right, so work it out. I'm going to pause in 5, 4, 3, 2, 1. All right, to work this one out, I had to find the rate of change first. Now remember, time is x and distance is y. So I noticed that from here to here, my time is changing by 14 seconds, and then from here to here, it's changed by 14 seconds again. And my distance is changing by 4, and then by 4. So I can see that there is a constant rate of change between these ones. For every 4 meters, it takes 14 seconds. So my change in y divided by change in x is 4/14, which reduces to 2/7. So we find her speed. Her speed is 2/7 of a meter per second. And it's probably better to write this as a decimal. So I said approximately, because I rounded, that's the symbol for approximately, 0.29 meters per second for that one. All right, and our last one. A clown rode in the race. So some goofy person goes into the race, and their equation is 20 minus x. Now what does that mean in terms of the race? Think of their starting place. Where are they starting the race? Think of their speed. What's happening to this clown in this race that is 20 minus x? All right, see if you can answer that. 5, 4, 3, 2, 1, pause. All right, so here's what it's telling me. This 20 right here is our intercept. This tells me that he's starting at the finish line. He's starting at 20 meters where the race ends. And then he's got a negative rate. A negative rate means that he is not going farther, he's going the other direction. So this guy is actually going towards the starting line. He's going the wrong way, basically. And the number in front of x, since there's no number there, is 1. So his rate is 1 meter per second, going in the opposite direction of all the racers. That's what the negative means. So if you plug it in at 1 second, he started at 20 and now he's only at 19. So he's going backwards in the race. At 2 seconds, he's at 18 meters. So you can see here that his distance is getting shorter as the race goes on, whereas everybody else is racing towards the finish line. He's starting at the finish line and going towards the starting line instead. All right, that's all I have for you today. We're going to finish off this lesson in our next video. All right, thank you very much. Bye-bye.